stream. So the stream is online. I will assign a new task. Please open the screenshot and then we will proceed. Or if you want, everything is already in Jamboard, the Jamboard. So we have finished our RNN. Meeting, I have implemented it by myself, tried that everything works. Also find some description to understand you. So how it mean like for from the overall, we see that conflict and why it is used. To determine that over and over again. So this one is update. As you can see, this is really blah, 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 blah. Copy all the information from the past and eliminate the risk of vanishing gradient problem. So this is the first why GRU is better than the vanilla RNN. Next one is the reset gate. we have to decide how much of the past information to forget. So which information currently won't be used. And we can see that this is already second line. Again, the same age, X, so, and bias. Again, all these three elements. Sigmoid at the end. Next one is current memory content. So we check what is in our memory at this moment, which will use reset key to start fast. Yes, we are getting it there. So again, we receive information which memory we reset it. So what is not required currently, we compare it with the X. Now we have updated memory. So what we need to store in memory, and we store it in our memory. We need to calculate information at the current unit, pass it on to the next one. Yes, so we update our memory. So those are basically 4 steps of the GRU unit that we will code today. So, okay, so have you opened? Okay, so I will show you here. So we have our equation that we need to implement. This one. This is just for you to better comprehend what is going on. So okay, I will open PyCharm. So you have okay, yeah, okay. So we have our RNN class. Please copy from class till the return. So basically copy the whole class. Yes, from the class till return of the forward. Please copy it. RNN, RNN. So copy it and place it below the RNN. So basically, you now have two RNN classes. Rename one as GRU. I just copied the class here. Is it done? Okay. Then additional step. In the model, where is the model? So just below model class. I remember I renamed the RNN class. I copied it and renamed GRU. So previously it was RNN, Now it is GRU. Okay? Okay. So now we have RNN class, GRU class. Now go down to the model class, copy paste the self RNN, or you can, if you want, you can just change RNN to GRU. So basically, okay, let's just make this as not RNN, but our GRU. Okay? Our environment. Then let's go to our GRU init function. Do you see the screen if I will do like that? Only you do not see this one. I will. I will. So I would not cut you. Okay, so I do not need that one. I have my pie chart window. So as we see, first equation is also based on that. This is LSTM. This based on that. There was update gate. So we need to update already existing information. So let's create new method. So after the init, let's make def update gate. So we have update gate inside which we want our X and previous hidden layer. So we want update gate XT and hidden. Currently would pass. So it wouldn't blame you. So you have now new function update gate. Now let's check out previous variables. Well, we changed them. So now we have VZ, UZ, and BZ. Let's change them. VZ, VH changed to UZ, and BZ. So currently you have three parameters. VZ, UZ, BZ. Any problems? Mm, previously it was like this, HD. But now I wanted to make sure that it goes like, so you understand the equations. Ah, okay, so now we have our weights for the update gate, our weights for the hidden layer, and bias. So let's now code in the equation. Basically, you can go, you can scroll down and copy those two. lines. So temporary X, temporary hidden. You copy them and put them just right below the update gate. So now our update gate calculates temporary X, self V Z by X, and our temporary hidden, not VH, but UH, by hidden. Sorry? UZ, yes, oh, sorry, UZ, yeah, correctly. So now we have calculated our X value, so we have our X value, we have our hidden layer value, and we have our bias. So now we are ready to return it with activation function. So place below return torch sigmoid and temporary X plus temporary hidden plus self bias Z. I will put this one inside Jamboard so you can have it. So okay, okay, we have it inside. Update gate is completed. So now we have ability to update our variables. Let's now use it. So go down where is our forward loop for X timestamp in X sequence. Delete those two lines as currently we do not need them. Hidden alpha can be commented out currently. And update gate values equals self update gate X temporary and our hidden. Might be if you want, it's much better to write it like xt equals and hidden. Yeah, let's be like that. So now we are calculating which values we need to update. Bless you. Is this okay? I need to show something. No? Yeah, sure, no worries. So previously we have no experience, so we will update everything. The first step is done. First gate is done, I would say like that. Okay? Okay. Next, since we have update, we need to have reset gate. So let's go up, copy update gate. Since it's equal, you can see that reset gate is basically the same, but with different parameters. So let's copy it, update gate, rename it to reset gate. So now we have two gates, but the only thing left, those are variables. Currently, they are the same. So we are sharing them. We do not want that. So I will write here. Update gate variables. Now I want to copy all the three. So VZ, UZ, and BZ. Copy them and rename it as VR, UR, BR. As here, we have VR, UR, BR. Yes? Sorry? Yeah. If you have copied it, just go down and change VZ to VR, UZ to UR. And yeah, BZ to BR. So now you have two gates. I will write this. with me. Right now you will have the infinite window by charm. Oh, nice. Sorry for that. I will show them slowly how our class looks like. So if you have implemented additional three variables, VR, UR, BR, you have implemented the reset gate. So you changed the BZ to VR, UZ to UR, and BZ to BR. We have done the second step, but we need to add it to the main loop. So after update gate values, we can even duplicate it and change reset gate values and change update gate to a reset gate. So now we have values, which one we need to update, which one we need to reset. If something isn't right, ask. Yeah? Yeah. Exactly. We had in the RNN we had VX, VH, BH. So now we have change those three to VZ, UZ, BZ, and copy them again and change them to VR, UR, BR. Okay, so now we have implemented two gates, which one will reset values, second one will update values. But now let's check out the equation. Now we have to combine them. So we have our VH, we have our UH, and we have our BZ. So we're reusing bias from the previous. So we need to create additional new variables, VH, UH. So now let's copy VH, UH, reset gate, not reset gate, but I would say memory update variables, VH, UH. In which step? I just defined new variables. Or you mean at this one? They will serve as additional weights for the X to update. You see, here we have our temporary hidden state will be tan h x times weights plus already our previous, so which values we need to reset times times previous history plus bz. So this will define uh, current memory state, basically. So you have your VZ, VR, and VH, correct? I need a confirmation from the class. Yes, no worries, no problems, yeah? Okay. Then we need another def. Let's call them current memory state. Bless you. Let's call it like that. One current memory state. Which variables do we need to pass inside? Let's check. We need to pass x, previous r, and the same hidden. So we need our x, xt. We need our r, which is reset gate, reset gate, or no, reset values. Let's name it like that. Which values we need to reset, and the same hidden. Okay, now let's implement the equation. So we have the same multiplication by VH. So let's copy temp x again. We have our temp x, but only by VH. Next one, we have our u by h. So let's copy straight ahead our h function. So now we're modifying UH. So the only thing is reset values. So next step is to multiply our reset values by current temporary hidden value. So we will name it blah, 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 blah. Reset state, let's call it like that. And we have, or no, if it is the same h, let's just keep it simple and tmp h multiply equals by reset values. So we have implemented that. Now we need to return activation function of tonnage from the whole sum. So we will return torch tonnage of our temporary x plus temporary hidden plus bias from z bz. So self bz. So now we have implemented 3 gates. I will update Jamboard in a moment. So now you have this one is where is so we have this inside. Okay, now what's left? Let's check the equation. We have our update values, reset values. Now we need to add our current memory state to our loop. So our hidden, let's name it hidden state equals to self current memory state, where inside is x t equals x t, so x timestamp. Next one, reset values equals reset gate values, and hidden equals hidden. So now we have implemented 3 rows of our equation. Any questions? I need something to show you from the previous one. Is everything fine? Okay, nice. Yeah. Okay. We can proceed. So now we have our update, reset, current memory state. We need to calculate what is hidden. So our hidden deleted. Now we have our z, so update gate values, multiply by previous hidden, so hidden, plus 1 minus z, 1 minus z, wait, so z is update gate values, multiplied by h, which are h, hidden state. So I hope that if we coded everything correctly, it will start to work. Yes? So, is it working? Okay, so we have it. It is working. It is fine. Now we can collapse GRU. Since we do not need them, I do not need GRU. Now we have our snip. We'll add forward. One moment. Okay, do LSTM. So I will open a new placeholder for the LSTM. Assign, assign. This one. We have a new template. Implement vanilla SLSTM without implement semicolon. So first one, implement vanilla SLSTM. Same template. So okay, let's. Is it working? Okay, I will check it in a moment. Here, Jamboard. Oh no, update gate values. If you want, if you do not want to press, just delete here or true. There was like or true, so delete this one. So we have successfully managed to finish the GRU unit. That's great. Let's check out what we have with LSTM. We have a bit more complicated structure. We have, I will delete this one since it's needed. And let's just, yeah, I haven't that long, but now I see. Okay, you have your PNG. Where is this stuff? Let's try to implement it. We can copy the same RNN or GRU. It basically doesn't matter. I will copy same class, the same this one. We have GRU and rename it with LSTM. So least short-term memory. Ah, sorry, RNN. Yes, yes. So now we have the same parameters, VH, VX. Let's check out. We should have VF, VI, VO, VC. Let's create them straight ahead. So we have VF, VF, we have VI, no, VI, yes, VI, we have VO, VC, VO, we have VC. So basically what we are doing, we're creating manually linear layers. So if normally you can skip this part with V blah 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 and just write torch and then linear, it's basically the same stuff, but we're just coding from the scratch. So we have VF, VI, VO, VC. Input hidden, input hidden, input hidden. Next, we need UF, basically the same stuff, but only with U. So we can delete so as needed. Now we need to previous one was the correct. No. We need UF hidden hidden. Yes, so we have now UF. We can copy it. 1, 2, 3. 1, 2, 3, and rename it to UC, UO, UI. So now we have our weight variables for the input layer. Now we have our variables for the hidden layer. Now we need to add bias. So the same thing with bias. So first one was BF, copy it. Sorry, WH. No, I replaced it with the UF. So we have our, I will add comment. We have our weights. We have our hidden weights. We have our bias. So we need BF, copy it again 3 times, 2, 3, 4, and change them to BC, BO, BI, BF. So I hope this is okay, no problems with that. Just look at the equation. You need to implement this one. Where is the pencil? VF, VI, VO, VC. Next one is UF, UI, UO, C. And the last one is B. BF, BI, BO, and BC. Sorry? So any problems with that? No, I hope that no. Because this one is, it's a shame to have a problem with copying in the student times. So yeah, we have 1, 2, 3, 4 for the input. We have 1, 2, 3, 4 for the hidden, and we have 1, 2, 3, 4 for the bias. Let's now check if we need to implement something else. FT we got, CT we have this one, ET we have, CT we have, H, OT, OH, that's sigma. Yeah, so we got everything. So let's now go down to forward loop. We will need same stuff, but how we can change it? How we can change it? We can either separate them or just write a long one for the whole. What do you prefer? Okay, then we either can separate it 1, 2, 3, 4 on the parts, or we can just write it as one sigmoid Being separate. Okay, then we will just copy paste those over and over again. But okay, let's use them as so temporary f. Let's temporary f, temporary f. We got our first part, so we got our f equals sigmoid. So torch sigmoid temporary f and xf plus temporary h plus self bf. So okay, we have completed one part for f. We can copy paste it and do the same thing for e. So again, we have e, 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 e. Change it with e, e, e. Basically, we can do it in the for loop too. But okay, e, 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 e. So we have implemented I. Let's now proceed the same with the O. So we have that for the O. Do not forget to change those as well. So VF, VF, U, F, V, I, U, I, O, V, O, U, O, 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 O. So we have completed 1/5. One. Next one is for the C, the last one. So for C, V, O, C, C, hidden for the C2, C, 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 C. So a lot of copy pasting. Just beware which variables you are using. Use the right variables for the right value. I hope that we do not have any problem here. So I will just quick check if everything is okay. I forgot to change the to LSTM, but okay. Okay, we have for our C, and now 1, 2, 3, 4. VF, VI, VO, VC. So we got our F, I, O, C. Let's see what we got further. Our C temporary. So our C temporary will be equals to ft, so our first value, f multiply. I only do not know what this notation means, but I think it's simple multiplication. You think it's a dot product? Dot product. Okay, well, I dot product dot f. Okay, let's currently keep it like that. I will check if there is an error, then we'll proceed further. C minus 1. So C previous. And what is C previous? We do not have this one. C previous, so our previous C value. Then let's make our C value is 0. I think that would be the right one. And then we are multiplying it. No, not C. Previous prev C. Let's name it like that. So we have our previous C times previous C plus our E times CT, so our C. This one should be okay. We should replace our previous C equals with our new, like that. Yes. And now we should have our H, so our hidden, to be equal OT, so O times sigmoid torch sigmoid from CT, so our CT. Okay, so let's check again our equation. So we calculate the F value using VF UF BF, VF UF BF, and using sigmoid. Yes. Next, E values, we calculate E sigmoid. O values, we calculate O. Next, C values, we'll calculate VC, UC, BC. Yes, we calculate the C value. Next, we calculate the CT, so FT by the previous one plus ET plus CT. Yes, we save our previous existing one. So since we go further, we need to save it. And our hidden layer is equals O times torch sigmoid from CT. A little bit up. One moment. Where? How much up? Okay. So now I think that we implemented the LSTM. So change the GRU unit to LSTM. Add it to the Jamboard or what? Yeah, for sure. Yeah, sure. I will only try to launch it. See. Error. It's working. Strange. Stranger things happen. So if we implemented everything successfully, everything works. I will add those missing parts. So you have the whole loop inside the Jamboard. So okay, we have finished that task. I think you should. We have created only a part of our task with LSTM. Let's proceed with that. What? Yeah, sure. This one, this one. Next, implement saving model at the best loss test value. So please try to implement saving at best loss test value. So you have your loss, just add one if. The tensor, the main function. So you have uh, four main attributes. Go through yourself F, I, V, delete that you go through the U and the same go through the B. And do not forget to name your class after LSTM. So you have LSTM. um, torch dot say. Okay, there were it was model. Oh. By torch save model save encoding model. Here it is. And path would be just model ETH. It was saved in this folder. So, but you need some condition. Yeah, so job was to create saving model at the best loss value. So let's initially, since we start the training, we do not have best. No, no. You just say, so we name the variable like best test loss would be um, what do you mean? No, I do not create a list. I want to create as a simple variable. So let's find if it's working, then yes. Also, you have the second part of the that you need to implement saving model. Yeah. So basically, what I want to put some really big number. So for example, let it be 10,000. Example, best loss function. Now I go down to where I need to save my loss. So I need if best test model, which is now equal to test to 10,000, is less than my current loss, I want to save my model. Uh, exactly opposite. If it's higher, yeah. If it's higher and I need to save the value, so best loss now equals to NP mean losses. And if I'm reusing this variable 3 times, I do not want to calculate it each time. So I just create test loss is equals to NP mean and reuse the same variable. So now we have that if model, then if our best test loss, which is now equal to 10,000, is greater than, for example, 5, then we will update our test loss and save our best model. Also, we can print statement just for us to see. So saved best model, test loss, and test loss. So I will run it. Because currently we have, one moment, I will check it out if it works. Save the best model, loss, blah, blah. So it works. At the best test loss value. loss, save loss, and because without screenshot is 50% lower. So what do you mean? Yes, 20. Yes. Ah, interesting stories are interesting when I have my presentation. Then I can say and express myself in many various ways. Not just thinking. Question? Huh? Okay. So the last one was implement new captcha classification. We'll see if we will finish it today. So I will open your new assignment, captcha classification. I will open it to template from English words. Dataset, okay. Model, model, moment. Now, yeah, is to implement model. We have our English words. English words. Pip install English word. We have now English words. Let's check out what we have. English alphabet. Device actually. Okay, we have our data set. Let's see what we have inside. Is it? Yes, we have random captcha example. Nice. Now we need to specify or build the model. I have an exit here, but if I will run eventually, I think that yes, I will. Yeah, because we don't have the model yet. So from our previous template, let's forward model. Try to copy RNN. I want to try whether it works. RNN. Bless you. I have ported RNN. Now we need to do a wipe in. Facts. Okay, let's make it a bit not so complex. We will use already implemented uh, momentum. So have you opened the template and uploaded and installed the packages yet? We need here. We need to extract features. So let's self encoder. So what will extract the features for us? Let's use already existing model search vision dot models dot resnet 18. So basically the same thing that we coded yesterday. Pip install English words. So basically you get name of this package where it was English word and pip install. So how are you installing Captcha install the same way? Huh? have English words. Now we need to fetch up features. So ResNet is the same concept, but we have implemented it yesterday. How many layers? So we want it pre-trained, let it be true. Next, we want our... Yeah, sure. Let's... Oh, let's change it a bit. Let's name this one as ResNet 18, and now we have self-encoder, torch, and then sequential, because we need to remove two last layers of the ResNet, which are classification and max pool. So we do not need them. We will cast it to list, ResNet 18 children, and we do not need last two elements. So we have our encoder. I will zoom out a bit here. We have our encoder. Next, we need LSTM model. Basically, we could use our model, but I'm not sure. So let's keep it with the already existing one, LSTM. So we will use torch and then LSTM. We will use already existing one. As you can see, everything is already inside. As you can see, there are the same functions that we have already implemented. So basically, everything is still the same. Sorry? Torch and then. So next, we need our input size, which is our input size, sorry. Input size. I do not know the input size yet, but I have my cheat sheet. Okay. Let's make it a little bit more intuitively right. This one commented. Let's add line to forward. So now we have our self encoder dot forward our x, and let's see which shapes do we have. Z dot shape exit. So we will check out what we have now. Which shape LSTM should take. LSTM have 512. 512. Now we can uncomment it and write 512 is the input size, hidden size 512, num layers, how many layers we want? 1, and do we need batch first? True. So we have defined our LSTM model. Much easier than the by hand, yeah. So num layers. Let's see what num layers is. Num layers, numbers of recurrent layers. Stacking would mean stacking two LSTM together to form a stacked LSTM. So now we have one, and if you want, we can add more. So we have our LSTM. Let's add it to our forward path. So we have our z equals, we have functional here important, torch and then functional as f. Please add that line as f. So we would not, I do not like to write one big sausage. So torch functional as f. Now we can go back and write, instead of torch functional blah blah blah, just f. And let's say we want adaptive max pool, and on our z with the kernel size for 1. So we have 4 in width, 1 in height. We'll go one by one. What do you mean? This is on what we want to perform, and this is the kernel size. So we have 4 by 1. Yeah. So again, we have our great adaptive pool. There was shape patch. Where is my run? Run patch 500 by 4 by 2. After that, we will have patch size 12 4 but 1. We have decreased our height value with the using adaptive max pool. Next, we want to squeeze it since we do not need that dimension. Z equals z dot squeeze minus 1. So we removed last dimension. Now we have patch 512 4. Next one, we want to again permute, as the previously we were changing the sequence, batch and sequence. So we want to do this again. Z permute. We're changing the channels. So now we have 0 to 1. We will multiply it. So now we have 0 to 1, which is batch for 512. Okay, now we have prepared the Z. As I see here, evals added, so we well, this is nice one. So we will add additional timestamp to process device 2. So currently we do not have end of line, end of string. So like you have string blah blah blah, but at the end you will have like a new line symbol. So we want to process that too. That's why we will add additional. We will increase the size of our timestamp by 1. Yes. Sorry. Because currently we have 4, and in that case our end of line symbol wouldn't be processed. Okay, let's add it. Z torch tag. So we already have our previous Z. Z torch zeros with the shape of zeros like the first dimension. We do not need that. We need the like this 1 2 and by first dimension. Let's check which shape do we have now. Previously I know the shape, but now print the shape. Now should be Torch, not stack, cut. Because we already see, we have 24, 4, 15, 12, and we got 24, 1, 512, and to stack them by already existing axis, we need cut. So now it should be working. Bless you. Yeah, so now we have added additional B5 512. Next one, we need to perform LSTM. So we already have all our features. LSTM out will be equals what LSTM returns. One moment, I will check. Forward, 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 forward. It returns two values, output and the permute hidden. So we do not want permute hidden, we want only our values. We do not need them, so that's why we can write, if we need them, we can write permute values, but since we won't need them, we can replace it with underscore, and Python will eat it with our self LSTM forward our z. What is the output? Our LSTM 24, so the same thing, it's processed. Okay. Next, we need to reshape it back. LSTM out reshape, let it be LSTM out dot reshape. No, not reshape. LSTM out continuous, as I remember it. Continuous and 2 as -1. Well, so we have prepared our LSTM features, which previously was like that. So now they are patch times 5. So we have created like that. Can someone name why we reshaped our features, our LSTM output? What is our final goal? So why we flatten? Why have we reshaped our model too much as to be as vectors? No, to perform a classification. So still we need somehow to text to tell that this IP is, for example, malware, or this captcha in our size contains this element A, B, C. Eventually, we want to break captcha, so that's why we're modifying it to later on feed into the linear layers. So we have prepared everything to be fed to our linear layers, but we need to create them. So self ff equals torch and then sequential. We will create small classification head. Eventually we want torch and then linear. As we know, our output was 512, so we can reuse it. 512 by 512, for example. Next, you already know why we apply a dropout to lower the possibility of dead neurons. Next, we apply normalization, batch norm, 1D, 12, and now we will add What's left? Leaky, torch, and then leaky relu, or it could be just relu, or it could be parametrical relu with your defined slope. So you need an activation function. Negative slope already is 1. Yes, so we have relu. Now we need another linear layer, which would input 512 and output length of our letters. So dataset full characters. We have it. And last one, probabilities. So which layer gives us the probabilities from linear layer? Dense layer is the same as linear layer. Excuse me? Sigmoid is activation function. So currently, sigmoid would be if we had another. We are using softmax, and we need to specify dimension. Last one. So we have created classification head, linear layer, dropout to eliminate that neurons, patch norm to stabilize the training process, activation function, and we have linear layer, which input layer input neurons 512, output neurons how many letters we have in our dataset, and softmax to gives us probability for each letter. Great. We have our classification head. Now we can go back to our reshaped function and we can pass it to our self yes ff dot forward lst lstm lstm. We have passed, and now let's check which what we have as an output. We have the shape of 120 by 30, and now we need to reshape back to match batch dimension. So eventually y prim equals y prim dot view -1 dataset full dot input captcha length and len of our dataset full dot characters. So let's check out the shape that we have now. Should be like batch size, captcha length 5 and 30. Batch 5, 30. So we have our shape, and I think that's it for the model. So we can try to command and try to run it. Now what we have, expected scalar long but found it in the loss function. Previously you haven't. Yes, please. One moment, I will add it to Jamboard and then I will come to you. Or it was your question? FF? Capital F? Functional. I just added, so I do not like to write all these things. It's much easier to write as a F. So I had an error like add Jamboard and then error. So you have it in Jamboard. Let's check out which error did I get. Expected long intro. You have the same error. Is it working for you? No? Oh, nice. So just add long here. So you need to add long post function by index is packed. It f means here. Search functional as f. now? You're free to go, yeah. As I remember, yes. Yes. Right, Captcha.